So for today, guys, okay, we're going to be going over universal gravitation. So this is essentially the start of this third of this unit. Okay, we break this up kind of into three parts: uniform circular motion, vertical circular motion, and then gravitation here at the end. Okay, so today we're just going to talk about Newton's universal law of gravitation, and then we'll look at applications of that in the coming days here, things like satellite motion and stuff like that. All right, but for today, we're just going to look at what Newton had to say about gravity. Now, Newton's given a lot of credit for this, but in the end, Newton never made it work. Okay? It wasn't until a guy named Cavendish came along and was able to run an experiment that effectively calculated the universal gravitational constant that Newton's idea became a reality. All right, so he kind of laid the groundwork for it, but it wasn't until somebody else came along that the idea actually worked for him. Right, and I'm not talking about the whole story that Newton told people about how he got hit in the head with an apple, because that's all garbage. He just made it up. Okay, so we need to learn the relationship between gravitational attractive force, force of gravity, mass, and distance. Okay, and then we're going to understand that gravity obviously can act as a centripetal force. We've already seen that kind of near the Earth's surface, but we're going to look at that also in terms of like celestial relationships. Okay, that is, things that are very far apart but are incredibly massive. They still obey kind of the same laws, so that's what we'll be looking at there. All right, so for an object to have weight, okay, for us to feel or to have weight, don't necessarily have to feel it, but to have it, okay, it has to be interacting with another object. Up until now, we've always looked at gravity based on its effect on the small object, because it's always been the Earth's gravity that has been pulling on the object. That is a very simplified view of what actually happens. Gravity is actually a mutual attraction between two objects. Okay, so my weight is actually the mutual attractive force between me and the Earth. The Earth is just as attracted to me as I am to it. Okay, so the Earth pulls on me with a force of whatever number of newtons, and I pull on the Earth with that same amount of force. The difference is that has absolutely no effect on the Earth, okay? But it has the effect of accelerating me towards the Earth at 9.81 meters per second squared. Okay, everyone all right with that idea? Yes? Okay. So what we're really going to look at here then is the true situation, and that is that the force of gravity is a mutual attractive force between two masses. So mass 1, mass 2, and then how far apart they are. Okay, that's Newton's universal law of gravitation. So the force of gravity in reality is the universal gravitational constant, that's this big G here, okay, times the two masses, me and the Earth, okay, and then the square of how far apart we are. R is like the radius or the separation distance between the two. All right, so if we're looking at various situations here on Earth, okay, on Earth, if I am standing at sea level at the equator, so right at the equator and I got my feet in the ocean, okay, I will have a weight of 684.6 newtons. If I go to the North Pole, I'm still at sea level, be a lot colder, okay, but I will have a weight of 688.3 newtons. Why am I heavier? I'm heavier at the pole than I am at the equator, but I'm at sea level in both places. Why am I heavier at the pole? Right, I'm closer to the center of the Earth when I'm at the pole, because the Earth's not perfectly round, it's still round. Okay, because those flat Earth people, crazy. Okay, it's just nuts to think that anyone still thinks the Earth is flat. Okay, the Earth's not flat. Okay, the Earth is not perfectly round. It's somewhat ellipsoid. Okay, and that has to do with the way that the Earth formed. Okay, the Earth is a spinning object. Okay, when it was molten, right, the the spin of the Earth meant that more stuff accumulated at the equator where the speed was the greatest, so the Earth all formed slightly oblong. In fact, most of the planets are slightly oblong. Okay, Saturn is a prime example. Saturn is very flattened, actually. Okay, it has very, very high speed winds, but it's quite a bit flatter. Okay, quite a bit wider at the equator than it is at the poles. Okay, but Earth is that way as well. Okay, if I'm in Chicago, I still weigh more than I do at the equator because I'm about halfway between. Okay, if I'm at the top of Mount Everest, this is a weird one. Okay, I weigh more on the highest point on the planet than I do standing at sea level at the equator. Right? So that tells you just how inconsequential Mount Everest is when we're talking about the size of the Earth. Okay, I'm further away from the center of the Earth, standing at sea level at the equator, than I am standing on the highest point above the Earth's surface. Okay, it is epic, but we don't think about it because, well, the Earth's round and consistent. Okay, but it's true. Okay, if I'm in low Earth orbit, okay, so on the International Space Station, I still weigh 647 newtons. I'm significantly lighter, okay, but I still have weight. If I didn't have weight, what would happen to me? I'd fly off. I wouldn't orbit the Earth. It's my weight that makes me orbit the Earth. If I didn't have weight, I wouldn't stay there. Okay? If I'm in high Earth orbit, that would be geosynchronous Earth orbit, where all of our GPS satellites are located. Okay? I would only weigh 15.5 newtons. It's quite a bit further away. All right, so what we're seeing here is that there are small decreases or changes in weight, okay, but as I start getting really far away, the changes become amplified. And that's because R in this formula it's squared. So there's an inversely exponential relationship between gravitational attractive force and the distance the objects are apart. Okay, so the further away from something you are, you will be exponentially less attracted to it. Don't try and make parallels sociologically speaking there. Okay? It has nothing to do with like long distance relationships and whether they'll work or not. Okay, it has to do with gravitational attraction. Okay, at this point, Mr. Dickey does something that makes all of his students feel really awkward. I actually watched him do it one day. He's talking about gravitational attraction and how the distance apart makes the attraction less. So he makes people look deeply into each other's eyes and say, I'm attracted to you, which is really awkward, okay, if you have to do that. And it's true, though, whether you're like, emotionally attracted to the person or not, you are gravitationally attracted to them, okay? You have mass, they have mass, masses create gravitational forces, and you are gravitationally attracted to each other. Fortunately, that gravitational attraction is tiny, all right? You can't attract a piece of dust floating in the air to you by gravity, okay? Even if it's this far away from you, you couldn't attract it to you due to gravity. It might be attracted to you due to electrostatic forces. They'd be way stronger, okay? But it won't be attracted to you due to gravity. The Earth's gravitational field kind of, takes over everything because the Earth is so big, all right? But it is true, okay? And so yes, because somebody once asked me this, so Coderre, if I kept eating, eventually it wouldn't matter that I couldn't move because food would come to me of its own accord? I'm like, I guess, theoretically, okay? You'd have to be, somewhere in the neighborhood of, half the Earth's mass for that to work, but okay, I'll buy that, okay? I don't know how you would get to that size, but yes, if you got big enough, food would be attracted to you, okay? Yeah. But in actual fact, is the food attracted to you? No, the food is, you and the food are mutually attracted to each other. Remember, gravity is a mutually attractive force. Okay? And this is actually what we use to detect planets around other stars. Okay? We initially use the dimming of the star, but we can also use the effect that planets would have on the star they orbit, okay, making it wobble. Right? The sun wobbles back and forth as the planets orbit it. Okay, because, well, there's lots of other mass out there, mainly Jupiter. Jupiter pulls on it the hardest because it's the biggest. Okay, but it can make the sun wobble back and forth. Okay, most of the exoplanets that we've discovered are what they call like super Earths or brown dwarfs. They're big big, like gaseous or really large things that orbit very close to their star. And so because they're very close and very big, they cause the star to wobble. Okay, the same is true for Earth and the Moon. Okay, which orbits which? Yeah, well, actually, they don't even orbit each other. They orbit a common center. Okay, the Earth and the Moon orbit a common center. So here's the Earth. Okay, here's the Moon. The Moon is way smaller than the Earth, and it's a long way away. Okay, but the Earth is attracted to the Moon, and the Moon is attracted to the Earth. We see the effects of that in the tides. Okay, the Moon does pull on the Earth. What we don't see is that as the Moon moves around the Earth follows it. Okay, so as the Moon is going around, the Earth moves a little bit towards it. So what happens is the Earth and the Moon actually orbit a point a little ways below the Earth's surface. So the Earth tries to orbit that point too, which makes it wobble, wobble, wobble around that point. All right. So if you could actually watch the Earth in its orbit, okay, from above. So let's say like here's the sun. Okay, the Earth's orbit wouldn't look like this. It wouldn't be a circle. Okay. It would be like somebody had taken a chunk out of a top and then spun it. Okay, the top would wobble like crazy back and forth because the weight wouldn't be distributed equally. So the Earth's orbit actually goes like this. Not that bad, but you get the idea. Okay, the Earth actually wobbles back and forth in its orbit. Okay, and it actually has points where it pulls away even further when other bodies in the solar system are near it. I say near it, but astronomically near it. Okay, when Jupiter is, on the same side of the sun as the Earth, okay, the Earth is going by Jupiter. Okay, the Earth moves a little bit towards Jupiter as well. Okay, and so on. So we get this effect of wobbling all the time. Right? They've actually done a bunch of computer modeling of the solar system and found that Jupiter is actually responsible for changing where the planets are over the course of the last 4.5 billion years. It actually has thrown Uranus and Neptune right out. Okay? It used to be way, way closer, but their gravitational interactions with Jupiter have caused them to accelerate and then be thrown, accelerate and be thrown, okay, and get further away, okay, over time. So there's a lot of kind of orbital dynamics and stuff that goes into how the solar system actually looks versus the simplified version we see. Okay, all right. Everybody follow me there. So the big thing we need to get out of this slide is the effect of separation distance and that the force between two objects is mutual. Okay. All right, so this is Newton's universal law of gravitation. Okay. Big G times m1 times m2 over r squared. Okay. Big G is the universal gravitational constant. It's on your formula sheet under other useful constants. Okay. Its value is 6.67 times 10 to the minus 11, and I'm trying to remember the units here. I don't even remember what the units are. They're beside it, I think, in your formula sheet. But okay, that's its value there, 6.67 times 10 to the minus 11. It's very, very small. It needs to be, because if it's not, basically it says that everything in the universe crushes everything else. Okay, the forces involved become incredibly massive because this number here, when it's plugged into this formula, shrinks the effect of the masses considerably. Okay, so we have to have it in there. It's what makes things work. It's the thing that Newton didn't have when he came up with his idea of gravitation. Okay, he explained his idea of gravitation with the apple story. Right? He was trying to explain to people how the apple and the earth are attracted to each other. Okay, which is why you can get hit in the head with an apple. Okay, it's not that the apple falls to the earth, it's they fall towards each other. You just don't notice the earth moving, okay, because the earth is so much bigger. He was trying to explain the effect that mass has on this force of gravity. Okay, so the earth is far more massive, obviously, than the apple, so the effects on the apple are more visible than the effects on the earth. Okay, everyone follow me on that line there? Okay, all right, so the problem for Newton is that this idea was great in theory, and you could see that his idea held up. The problem was the math never worked, okay? Because when he tried to do the math without big G, he was finding that the forces on the apple were just ridiculously large, okay? And so he could never make this work. And the reason he couldn't make it work was because he couldn't ever calculate or measure what big G was because Earth's gravity always interfered. Earth's gravitational field is massive, okay, and interferes with basically any experiment he could think to run. So what ended up happening, is a guy named Cavendish developed this experiment. Okay, what he did is he made all the forces in this experiment perpendicular to gravity, so that gravity couldn't affect his results. Right? So he built what's called a torsion balance. Now, he didn't have a laser, because this was way before lasers. He just had a light beam. Okay, and what he did is he had these big lead spheres, and they were on a bar, and that bar essentially couldn't move. Okay, then he had a torsion fiber, so a very thin wire, a very light, thin wire that he hung down from the roof. Okay, on that torsion fiber was a mirror and two very small spheres made of like cork or pith, really light material. Right? So by comparison to the lead, they were very, very small. Okay? So what he did is he hung this and he made sure that basically there was nothing that could cause the fiber to move, these two things to move, except for their gravitational attraction to the larger lead spheres. Okay? Because this was hanging, the forces were horizontal. Earth's gravity works vertically, so it couldn't interfere with the experiment. So what he said is, if gravity is dependent on what Newton said it is, then this ball should move closer to this sphere, and this ball should move closer to this sphere, which will cause the torsion fiber to twist. Okay, and so if it twists, then his light beam would be deflected onto this screen, and he would be able to measure the angle that it twisted. Okay? Since he knew what that torsion fiber was made out of, he would be able to calculate from that angle how much force was being used to twist the wire. Okay? That twisting force, okay, or torque, would be equal to the force of gravity between these masses. All right? So what he was saying was, I'm going to have this number that I know, I'll make it equal to the force of gravity, okay, and that'll be mass 1 times mass 2 over r squared with this thing that Newton couldn't calculate. Since he knows what the masses are, and he knows how far apart they are, okay, he could get that missing number. Newton could never get that missing number, because okay? He could never get this force, because Earth's gravity always interfered. Everybody follow? Okay, and he also never could measure the radius of the Earth effectively either. Right? He never had a really good explanation for that, or a good number for that would work reliably. Okay, so Cavendish eliminated the Earth as a source of problems, okay, and did it this way. Right? So this is Cavendish's torsion fiber experiment. Put a thing beside it. It's important, okay, because it allowed us to calculate the gravitational constant. Okay, here's the units, right? Newton meters squared per kilogram squared. Strange units. Luckily, you never have to remember that. See, even I don't remember it. Okay, but the value there, okay, 6.67 times 10 to the minus 11, that's what Cavendish was able to calculate with that experiment. Okay, this graph here, guys, is showing us what happens to the force of gravity with increasing distance. Okay, and we see an inversely exponential curve there, okay, because obviously, if r is squared and we're dividing by a number that's getting exponentially larger, then our number will get exponentially smaller. Okay, everybody all right with that? All right, so let's try this one here. So not that astronauts would do this, but let's say they took a watermelon or a cantaloupe to the moon. Okay, so they take a melon, a big piece of fruit, to the moon with them. Okay, its mass is 0.65 kilograms. What's its mass on the moon? 0.65 kilograms. Mass is not affected by gravity. I have put that as a multiple choice question many times on this unit exam. A lot of people get it wrong. Okay, guys, mass is how much of you there is. Don't forget that. Okay, your mass doesn't change depending on where you are. Even in zero gravity, you still have mass. Okay, so its mass is 0.65 kilograms. The mass of the moon is 7.36 times 10 to the 22 kilograms. And the radius of the moon is 1.74 times 10 to the 6 meters. What's the weight of the melon on the moon? Okay, so usually we do this if we want to find weight. Problem is, I don't know what this is on the moon. Okay, so I can't use it. So what I'm going to use instead is Newton's universal law of gravitation, because that will work anywhere, regardless of whether I know what little g is or not. So I've got FG equals big G times the mass of the moon times the mass of the melon. Oh, those both start with E. Okay. Divided by the radius of the moon squared. All right. So when I plug in my numbers, that's going to be 6.67 times 10 to the minus 11 times 0.65 times 7.36 times 10 to the 22 divided by 1.74 times 10 to the 6 squared. What do you suppose the thing is people forget most often when using this formula? Squaring R. Okay, guys, should you know right away if you have forgotten to square R? Yeah, if like I ask you to calculate something near the Earth's surface and it's, you know, something small and you get a stupidly big number, you probably forgot to square R. Okay, you'd be surprised how often I have people write those answers down regardless of how silly those answers seem, okay, without double checking. All right, so when we do this, we're entering it into the calculator. It does become a lot of number punching, okay? And it's going to involve some brackets as well if we're going to make it work right. All right, so we got 6.67 to the negative 11, okay, times 0.65 times 7.36 E22 divided by 1.74. All right, so it weighs 1.1 newtons on the moon. All right, compared to what it would weigh on Earth. Okay, which would be almost 6.5 newtons on Earth. Okay, so we're looking at that the acceleration due to gravity on the moon is about 1/6 of what it is here on Earth. Okay, if I do Newton's universal law of gravitation, his big formula, instead of m times g, should I get the same number? Right? Theoretically, I should get the same number. Right? Let's see if we do. Okay, but now I have to use the Earth's mass. So 5.98 E24 and the Earth's radius. I'm drawing a total blank. It's 10 to the 8. But 6.38 times 10 to the 6? 6.37 times 10 to the 6, right? Okay. Wow. No, the 10 to the 6. I put 7 there. 10 to the 6, right? Okay, and oh, that's got to be divided. I screwed up. Oh. And that's got to be squared. Okay. So when I went 0.65 times 9.81, I got 6.3765. When I did Newton's universal law of gravitation, I got 6.389. Why am I not getting the same number exactly? Getting around the same number. Okay. When you look on your formula sheet there, when you looked up the Earth's radius, what does it say beside the Earth's radius? Average Earth radius. Because remember, the Earth's not perfectly round, right? The average Earth radius is different depending on where you are. And is 9.81 a value that's true everywhere on Earth? No, it's also just an average value. Okay, so we're taking two numbers that are not entirely true and then trying to calculate the same number with them. So we're not going to be entirely successful. We'll be close, but not entirely successful. Okay. Right? These are the kind of calculations that JPL has to do, okay, when they're trying to land something on another planet, except they've got to use the real values. They can't go, oh, well, the average radius of Mars is this much, and then try and land a lander where they want to. Okay? they try and do that, that's when they get a smoking crater instead of an effective lander. Okay, they have to know all of those real values so that they don't make mistakes that seem, oh, it's just a hundredth, right? It's not a big deal. It is when you're landing $1 billion spacecraft. Okay, those little numbers mean a lot. All right, so this is what we just did here, basically just plugging in the numbers. It's not a difficult formula to use. Okay, what becomes crazier is when we have to set it equal to something else. Then the manipulations become a little more intense. Okay. All right, so Newton's first law says that an object should travel at a constant velocity, okay, forever in the absence of forces. Okay, if there is an unbalanced force, then the object will accelerate in that direction. So an orbit is actually the product of those two things going on, an object's inertia and the fact that it's attracted to something else. Okay, so if we're looking at the Earth and the Moon, let's say, so the Moon will be this little black dot here, and this will be the Earth. Okay, the Moon wants to travel in a straight line, but it's gravitationally attracted to the Earth, so it accelerates towards the center of the Earth. But it's got a lot of speed that wants to go in a straight line, but it's gravitationally attracted to the center of the Earth, but it wants to go in a straight line, et cetera, et cetera. Okay? The product of those two things going on at the same time is a circular orbit. Okay? Centripetal force balancing the inertia of the object creates a circular path. Okay? That's how we get something to orbit something else. Now, if something wants to orbit something else, it's got to go fast. There's a minimum orbital speed that has to be accomplished. That's what was giving people trouble during the early days of the space race. Okay? Early days of the space race, the biggest problem with getting something to orbit the Earth was making it go fast enough to do so. Okay? That's why we had to build more and more powerful rockets, okay, in order to get things to move that fast. Okay? Who accomplished it first? Yeah, Russia. Okay, they got Sputnik into orbit first. Okay, and Sputnik orbited the Earth. Okay, making a beeping sound that scared the ever-loving crap out of everyone who was part of NORAD. Okay, because what did they automatically think once they got something into orbit? Yeah, if they can put that little ball into orbit, they can put a nuclear warhead into orbit, which means they can hit us anywhere, anytime they want. Okay, that was the line of thinking. Okay, and it's actually true. Okay, nuclear weapons do, if they're on missiles, actually go out of the Earth's atmosphere and then come back down to hit their target. Okay, the intercontinental ones, that's what they have to do. All right, so they were absolutely right about that. They had every reason to be afraid. Okay, when that first happened. Okay, but to get something to orbit the Earth, you have to make it go really fast. Okay, so that was the big stumbling block at first. All right, so this is just the explanation of what we just did here. If there was no gravity, things go in a straight line. There is gravity, so they're attracted in. Okay, that produces the circular path. All right, so what we want to do here, guys, is let's figure out how fast the Moon is moving in its orbit around the Earth. Okay, figure out how fast the Moon is moving in its orbit around the Earth. All right, so what's keeping the Moon in orbit around the Earth? Their mutual attractive force of gravity. Okay, that's providing the centripetal force that keeps it in orbit around the Earth. So what that means is that mv squared over r equals Newton's universal law of gravitation, g times m over r squared. Okay, I got 3 m's in this formula I've just made, but I'm only talking about the Earth and the Moon. So I can easily do this, Earth and Moon, and then this radius would be the distance between the Earth and the Moon. What's the other m? So when we use this formula, it's for something that's moving in a circle, right? Okay, so in simplified terms, which of the two is moving in the circle? The Moon, right? The Earth is moving in this, it's orbiting that point that's under its surface, but for all intents and purposes, this is the Moon. The Moon is the thing that's moving in the circle. Okay, so mass of the Moon is actually on both sides of the equation. And that's true for all satellites. Okay, it actually doesn't matter how big a satellite is. The speed it has to move at to orbit is the same regardless. Okay, the speed of an object that needs to orbit is only dependent on how far from the Earth you want to put it. It has nothing to do with its mass. Okay, I want to calculate how fast the moon is going. So I need to move this r over to this side. So I'm going to multiply both sides by r. That's going to make this r cancel and this r go away. Okay, so those are gone. The squared is gone. Okay, I'm going to divide both sides by the mass of the moon. Good, that'll cancel. And then I'm going to take the square root. Now I'm solving for the speed of the moon. Everyone follow what I did there? Okay, all satellite motion sets up just like this. Fc equals Fg, mv squared over r equals Newton's universal law of gravitation. All right, so V will equal, okay, the square root of 6.67 times 10 to the minus 11 times the mass of the Earth, 5.98 times 10 to the 24 kilograms, divided by 1.85 times 10 to the 8, average Earth-Moon distance. 3.8 times 10 to the 8. Okay, and we already canceled the square, so we don't need to square that. All right, so we're going to plug that in. Now, how you decide to do this, okay, is going to be entirely up to you, but know that it gets crazy if you're like trying to do it all in one step. Keeping track of all your brackets can start to be a problem, right? So what I usually do is I do the square root after. Okay, so the moon is moving at 1,017 meters per second as it orbits the Earth. 1 kilometer per second. Is that fast? It seems fast. I mean, if you were on Earth, that would be really fast. Okay, and some objects can travel that fast through the Earth's atmosphere. Not very many, but some. Okay, but if we're talking about the moon and its orbit around the Earth, it still takes the moon like 28 days or so to go all the way around the Earth. Okay, so even though it's moving at a kilometer per second, okay, it has a pretty large distance to cover. Okay, all right, everyone follow what we did there? Okay, that's going to be a very common thing that you'll be asked to do. Okay, so gravitation is a big deal when we're planning to send spacecraft to other places. The biggest challenge sending spacecraft to other places in the solar system is fuel. Fuel is heavy. And we have to get things obviously off the Earth's surface in order to get them somewhere else. Per kilogram, okay, that's an incredibly expensive venture. So we want to send small spacecraft with small amounts of fuel. But we need those spacecraft to go fast. So we either need engines that don't need a lot of fuel, okay, kind of like New Horizons has a it's the fastest moving human object ever. Okay, it's got special engines that require very little fuel. It also got put on the most powerful rocket we have. Okay, and that got it moving very, very fast. However, that's not the only place it got its speed from. What else did it do? It slingshots. Okay, the gravity slingshot is something NASA uses all the time. If you've seen The Martian, they used it in order to send themselves back to Mars. They did a gravity slingshot around the Earth. Okay, the gravity slingshot uses acceleration due to gravity from a massive object to accelerate a small one. Okay, now you got to remember though that this force of gravity is mutual. So while one object is speeding up, the other is slowing down. When it's a big planet, we don't worry about that too much, okay? But we've been using Jupiter to do gravity slingshots to the outer solar system since we started going there, okay? We keep slowing Jupiter down. Not very much, obviously, Jupiter's huge, okay? But each time we do it, Jupiter slows down just a little bit, okay? Because we are stealing some of its gravitational energy, right? But basically everything we've sent out, okay, you can see here a lot of these paths, they go around Jupiter, right? They're using a gravity slingshot to send them out to the outer planets. Every time we go around a planet, we do a gravity slingshot, okay? Not just to pick up speed, but also to help us alter course without using fuel, because to turn requires fuel in space. Okay? We don't want to use much fuel, so we use the gravity slingshot to help us change course as well. Because we don't just go, all right, I'm going to come in, I'm going to go all the way around Jupiter and go right back out again. If I do that, do I gain anything? Right? I'm getting close and then I'm getting further away. I'm not really going to gain as much as if I come in a little bit and then shoot off. Because of the way these are drawn, it looks like we do that every time, but it's not. Okay. The solar system's never in line like that. Okay, so we go partway around Jupiter and use it to shoot us off in another direction at a higher rate of speed. Okay, so what you see here, guys, is every single tiny line represents one mission sent from Earth to somewhere else. Okay, so obviously the most often visited place is the moon. Okay, we've sent more stuff to the moon than anything else. Okay, second most visited place would be Mars. Okay, third be Venus. Okay, we haven't sent much to Mercury, only a couple because there's not much to see. Okay, and then we've obviously sent a few to the outer solar system as well. But you can see there's a banding pattern here. Okay, light colored lines are successes, darker failures. Okay, so the moon, yeah, we got a pretty good track record going to the moon. Okay, it's a lot closer. There's a lot more bright lines. Okay, Mars. Successful landing on Mars after Monday, when we got another one, okay, is still below 50%. Okay, we can get missions to Mars, like into orbit. That's less of a problem, although some of those still fail. Okay, but actually landing something on another planet is very, very difficult. Okay, and on Mars, the success rate is less than half. Okay, there's so much that can go wrong. There's so much that can go wrong, and what's the other problem? Okay, I had the InSight landing playing in here on Monday at lunch and in period 3. Okay, I had it playing when they actually landed it. There's an 8-minute delay between what you see happening and what's actually happening. Okay, so there's this point where the people at mission control have to go just hands off. The spacecraft has to land itself. They can't do anything because by the time they know something's wrong, it's too late to do anything about it. Okay, so while we were watching the live feed, okay, it was a case of Schrodinger's cat. Okay, either the spacecraft was a smoking crater or it was safely on the ground, but we wouldn't know for another 8 minutes. So we watched everything unfold, but it was already done. Okay, and so there's nothing they can do to change course or do anything like that that can help the spacecraft because it's 8 minutes to get to them and it's 8 minutes to send the response back. Okay, well, it's too late by then. So, so that's the main difficulty with landing something on another planet is it has to be done by the computer. The computer has to do all the decision making. Okay, and sometimes they don't always make the right call. Okay, or something goes wrong and there's nothing they can do. Okay. But yeah, we got another lander successfully on Mars that is going to study the interior of Mars now. So they're going to use waves, seismic waves and stuff to study what the interior of Mars looks like as opposed to just the surface. All right, and then we got all these gravity slingshots here that go out to the outer solar system. Okay, like we say, stealing some energy using Newton's universal law of gravitation as well as conservation of momentum to get us out there. New Horizons is now way beyond Pluto. That's the one that took the pictures of Pluto. Did you guys all see those? 2015 flew by in August. Okay, on New Year's Day, it's going to fly by the most distant object ever visited. Okay, and it's a Kuiper belt object called Ultima Thule, and it's just like a comet fragment or something. They're going to go by, and they're going to do that in January. Okay, so it's still doing science, but it's still got an incredibly high rate of speed. Right, so basically it'll be like Pluto. It'll be like, okay, get the cameras ready, don't blink, you'll miss it, and they'll be passed. Okay, because they're going so fast. All right, so we did that math there already. Okay, I want you guys to try this one here. Okay, so it's a Newton's universal law of gravitation thing. Okay, so it'll be this formula. Okay, I want you guys to calculate the difference in weight between the bottom of Mount Logan and the top of Mount Logan in Alaska. Okay, so it sounds like a few people are getting this finished here. So really all we have to do in this question is do this calculation twice the second time around, we're going to add the height of Mount Logan to the radius of the Earth, because we'll be that much further from the center of the Earth on the top of Mount Logan. Okay, so in our first calculation, then we'll have 6.67 times 10 to the minus 11. If we're using their numbers, which are different than what on your sheet, okay, mass of the person, 55. Okay, then the mass of the Earth, they have 9.7, but it's 5.98. Okay, times 10 to the 24. Okay, then we divide that by the Earth's radius, which they also have as a different number than ours. Okay, we'll use ours except for this question. Okay, so we do that calculation, we're going to get a number. In the second calculation, we simply add 5,959 meters to that number and do it again. And what we find is there's really a difference of about 1 Newton, okay, between the top and the bottom of Mount Logan. Not something that you would likely detect, especially since climbing to the top of Mount Logan would result in you losing mass because it's incredibly hard work. Okay, you would be lighter at the top of Mount Logan because there's less of you there than there is at the bottom. Okay, because you'll have lost a lot of weight, okay, in doing that, not because you're further from the center of the Earth significantly. Okay. All right, everybody okay with that one? So it's really just 2 calculations of Newton's universal law of gravitation, just changing this radius number. Okay, and it doesn't change it very much. Okay. I want you guys to try 1 and 2 here. Okay, they're just universal law of gravitation questions. Okay, we're not setting it equal to anything right now, just trying to figure out some variable within it. So realistically here, guys, Newton's universal law of gravitation is not a really difficult formula to use. Okay, it's just a matter of deciding when to use it. Okay, manipulation's also not all that difficult. You just have to make sure you plug it into your calculator correctly. That's where the real challenges come, is just making sure you get your brackets right, you remember to square things and stuff like that. Okay. All right. So the purpose of this question here, guys, is to show you that again, the relationship between mass and force of gravity and radius and force of gravity. So remember, the formula looks like this: Fg equals big G times mass 1 times mass 2 over r squared. Okay, so any change in mass results in a linear change in the force of gravity. If I double the mass, there'll be twice as much gravity. Okay, if I double the radius, there'll be how much less gravity? Yeah, 4 times less, or 1/4, okay, because it's inversely exponential. All right, so this question here is basically just trying to manipulate that a little bit. They're saying you've got object A exerting a gravitational force of magnitude 1.3 times 10 to the minus 10 newtons on object B, which actually isn't true. It's not A exerting it on B, it's mutual. Okay, they're exerting it on each other, and that is really the way it should be written. Okay, determine the magnitude of the gravitational force if the separation distance is doubled. So r is 2 times bigger. Okay, mass A increases by 6 times, and mass B is halved. Okay, now most people look at this question and go, I don't have the first clue how to start that. I don't have any numbers. And I feel your pain. It's frustrating if they ask you to do something and they haven't given you any numbers, right? But there's a way around it. I'm just going to figure out how many times bigger or smaller this is by, instead of inserting numbers, by inserting these factors instead. Okay, then I'll get a number here that's not a force of gravity, but is a factor for how many times bigger or smaller it is now. Okay, so I'm just going to go 6.67 times 10 to the minus 11. That's the only number I'm actually going to use. Right? They said they're going to make mass A 6 times bigger, so times 6. All right, and then they're going to make mass B half as big, so times 0.5. And then they're going to double R. So I'm just going to put a 2 there and square it. Right? Now, I'm obviously not going to get the actual force of gravity, but I'll know if I get a number greater than 1, it's going to be bigger. And if I get a number that's a decimal, then it's going to be smaller. Okay, so we'll have our 6.67 e negative 11. Whoop, 11. All right, times 6 times 0.5, and then divide that by 4. Okay, so, oh, sorry, I wasn't supposed to put this in. What was I thinking? I wasn't supposed to put that in. Sorry. I don't know why I put that in, guys. Looking at that going, wait a minute, that doesn't make sense. Okay, so even without the math here, okay, if I just look at this, what's 6 times 0.5? 3. And on the bottom is 4. What's 3 over 4? 3 over 4, yeah. 3/4, right? Did the force get bigger or smaller? Smaller. I have 3 times as much mass in the second situation, but I have less gravitational force because they're twice as far apart. Okay, so even though I made more mass, considerably more, okay, the effective radius is greater than the effective mass. Okay, everyone all right with that? Okay, so that's all that's trying to illustrate. I would never ask you one like that because I don't think there's much of a point other than to illustrate. I don't need you to illustrate something to me on a test. Okay, so it illustrates to you. Okay, so number 1 here, similar idea. Okay, so they're saying you got these 2 objects here, and they exert a certain amount of gravitational force. Okay, they increase the separation distance now to 4 over 3. Okay, of its original value, and increase 3 over 2. Separation distance of its original value. Mass A increases 1.5 times, and mass B is halved. Okay, so we have more separation distance, and we have more mass. Which ones is this going to be, more or less force? Less. Okay, we're going to have less force. Again, yes, we increased the amount of separation distance, not by as much as we increased the mass, but this has a bigger effect. And that's all that question is asking you to be able to do. Okay, and we're not looking for an actual number here, just to be able to kind of understand that in our heads. Okay, all right. Now, this is one that often comes up, okay, with universal gravitation, because it goes back to Unit 2 with net force. Okay? If I want to calculate the net force on the Earth right now, how many forces are acting on the Earth? No, just in this situation here. 2. The attraction between the Earth and the Sun, and the attraction between the Earth and the Moon. Those are the 2 forces acting on the Earth right now. Okay? So how would I calculate the net force here? And then just subtract, right? So I'd find the force of gravity between the Sun and the Earth. Okay? That would be big G times the mass of the Sun times the mass of the Earth divided by the radius of the Sun and Earth squared, and then do the same thing for the Moon. Okay, so big G times the mass of the Earth, mass of the Moon, okay, radius of Earth, Moon. Okay, subtract those 2. Why am I subtracting? Well, yeah, they're in opposite directions, right? The Moon is on the other side of the Earth from the Sun right now. Okay, this is when we get like the really red looking moon. Okay, when the Earth moves between them, we get the really red looking moons. Okay, all right, we're going to look at that one tomorrow because I can't remember the last time I didn't put a question like that on the unit exam. I can't remember the last time I didn't.